the light that should not be the gamma-ray burst detection system aboard the Neil Gehrels Swift Observatory operates continuously, scanning the entire sky for sudden bursts of high-energy radiation. Swift was launched in November 2004 specifically to catch these events, which are the most energetic explosions in the known universe since the Big Bang itself. A typical long gamma-ray burst occurs when a massive star, one with at least 20 times the mass of our Sun, exhausts its nuclear fuel and collapses into a black hole. The collapsing core generates two tightly focused jets of radiation that blast outward at relativistic speeds, and for a few seconds to a few minutes, a single dying star outshines the combined light of every star in its host galaxy. The physics of this process is well understood. The duration, the spectral properties, the afterglow behavior, and the host galaxy characteristics of gamma-ray bursts have been cataloged across thousands of events. We know what they look like. We know what they should look like. On March 30, 2026, Swift detected a gamma-ray burst designated GRB 250702b. The James Webb Space Telescope turned its instruments toward the source within hours, and what it recorded has been described by the lead author of the subsequent paper as, in their precise words, an extraordinary event with no clear counterpart in our existing theoretical framework. This is where the terror begins. GRB 250702b lasted approximately 40 seconds, placing it firmly in the long gamma-ray burst category associated with the collapse of massive stars. But the afterglow behavior, the fading emission that follows the initial burst as the jet plows through surrounding material, did not follow the standard model. The optical afterglow faded far more slowly than any known physical mechanism predicts for a burst of this type. The X-ray afterglow showed rebrightening episodes at intervals that do not match any model of jet structure, cocoon breakout, or magnator spin-down that has been proposed in the literature. The host galaxy, identified by Webb in its near-infrared channels, is a massive, heavily dust-obscured system with a star formation rate that places it in the category of ultraluminous infrared galaxies, objects so enshrouded in dust that most of their radiation emerges in the infrared rather than in visible light. This is unusual for a long gamma-ray burst host. The standard model associates long bursts with specific types of young, lematolicity galaxies where massive stars form and die in predictable ways. The host of GRB 250702b is none of those things. The paper reporting these observations, published in the Astrophysical Journal Letters in late March 2026, lists multiple possible progenitor scenarios in its abstract, which in the language of scientific literature is a signal that none of them is satisfying. The scenarios include a highly obscured standard collapsar in an unusual environment, a merger of a neutron star with a massive star, a magnetar giant flare from an extraordinary distance, and, noted last and with the most careful hedging, an unknown progenitor mechanism. When a paper in a refereed astrophysics journal uses the phrase unknown progenitor mechanism, it is not being modest. It is being accurate. The specific property of GRB 250702b that most directly challenges existing physics is its energetics. The isotropic equivalent energy of the burst, the energy that would be implied if the radiation were emitted equally in all directions rather than in focused jets, is approximately 3 × 10 to the 14th ERGs. This is one of the highest values ever measured for a gamma-ray burst. But the host galaxy redshift, measured precisely by Webb's NIR SPEC instrument, places the event at a distance corresponding to a look-back time of approximately 9 billion years. At that distance, the observed fluence of the burst translates to a true energy release, accounting for the beaming factor derived from the afterglow jet break. That exceeds what any current model of stellar collapse can produce without requiring either an implausibly extreme initial spin for the progenitor star or a beaming angle so narrow that the probability of observing it from Earth is formally negligible. Both explanations exist in the literature. Neither is comfortable. Together they constitute the theoretical equivalent of saying, we do not know what produced this. The connection to the Fermi paradox is not metaphorical. It is mathematical, and it runs through the physics of gamma-ray bursts and their role as sterilization events. A long gamma-ray burst occurring within a few kiloparsecs of a planet-hosting star system will deliver sufficient gamma radiation to strip the ozone layer of any Earth-like planet within its beam, rendering the surface lethally irradiated and potentially triggering a mass extinction. This has been proposed as a partial explanation for the Cambrian explosion and for the Ordovician mass extinction event in Earth's own history, during which roughly 85% of marine species were eliminated. The relevant calculation is straightforward. The Milky Way produces approximately one long gamma-ray burst per million years. The beam of a typical long burst subtends a solid angle of roughly 1% of the sky. A planet in the habitable zone of a star within 3 kiloparsecs of a burst and within the beam receives a lethal dose of radiation. Applying these numbers to the stellar density of the galactic disk over the timescale required for complex life to evolve, the probability that any given planet survives 4 billion years of galactic gamma-ray burst activity without at least one civilization-ending irradiation event is low, not zero, but low enough to constitute a meaningful statistical filter on the development of technological civilizations. GRB 250702b complicates this picture in a specific way that has not been discussed in any public communication from any space agency or press office. The burst occurred in a heavily obscured, high star formation galaxy at 9 billion years look-back time. This means it occurred when the universe was approximately 4 billion years old. It means it occurred in exactly the kind of environment, a dense, actively star-forming system with high rates of massive stellar death, that would be expected to produce frequent gamma-ray bursts. It means that the epoch of cosmic history during which the first potentially habitable planets were forming around second and third generation stars was also the epoch during which gamma-ray burst rates were highest because star formation rates were highest. The two processes, planet formation and sterilization by gamma-ray bursts, were not merely coincident in cosmic time. They were driven by the same underlying mechanism, the availability of heavy elements from previous stellar generations, which simultaneously enabled rocky planet formation and enabled the formation of the massive, short-lived stars that produce gamma-ray bursts. The window during which the first complex life could have emerged on the first habitable planets in the universe was also the window of maximum gamma-ray burst frequency. The universe did not merely fail to provide a safe environment for the first potential civilizations. The physics that made civilizations possible was the same physics that made their sterilization frequent. GRB 250702b, with its anomalous energetics and unknown progenitor mechanism, adds a further complication. If the standard model of gamma-ray burst physics, which has been calibrated on thousands of events and refined over decades, cannot account for the properties of this single burst, then the statistical models built on that standard physics are underestimates. The true diversity of gamma-ray burst types and the true upper end of their energy distribution may be broader than the catalog of observed events suggests. Every event that defies the standard model is a data point indicating that the tail of the energy distribution is heavier than the models predict. A heavier tail means more extreme events. More extreme events mean higher sterilization probabilities at greater distances. Higher sterilization probabilities at greater distances means a more efficient filter on the development of complex life across cosmic time. The Perseverance rover on Mars and the TRAPPIST-1 system observations by Webb represent humanity's most direct current searches for evidence that life is common in the universe. Both searches are motivated by the implicit assumption that the physical environment of the universe is broadly permissive, that the conditions for life are common because the ingredients are common, and that the silence of the cosmos is therefore a puzzle requiring explanation. GRB 250702b and every other gamma-ray burst that defies our models is a data point on the other side of that assumption. The physical environment of the universe is not broadly permissive. It is intermittently violent in ways that our models cannot fully capture because the extreme events are rare enough to be undersampled and energetic enough to be decisive when they occur. The silence of the cosmos may not be a puzzle. It may be a consequence of physics that we are only now beginning to measure at the energetic extremes where the models break down. The civilizations that should be filling the galaxy with signals, the civilizations predicted by the Drake equation and the Kepler exoplanet statistics, are absent. The explanation that gamma-ray bursts provide is not complete. Sterilization rates alone cannot account for the total silence across all of cosmic history. But every anomalous burst, every event that exceeds the predictions of our standard model, is a reminder that we are calculating the habitability of the universe using models calibrated on the subset of events that we have measured, and that the events we have not measured The ones too extreme to be common and too energetic to be ignored are the ones that set the ceiling on how long civilizations can survive. GRB 250702b is not the most energetic burst ever recorded. It is not a unique anomaly in a well-understood distribution. It is an event that our best models, built from the most comprehensive catalog of gamma-ray burst observations in history, cannot explain. And its host galaxy, buried in dust 9 billion years in the past, in the epoch when the universe was building its first truly habitable worlds, was not a quiet place. It was exactly the kind of environment where civilizations, if they were forming, would have had the shortest time before something like this found them. We are not the first civilization to look up at the gamma-ray sky and calculate what it means. We are simply the latest, and the calculation does not get more reassuring with better data.